Welcome to this explainer on advanced battery chemistry. We are going to completely skip the boring basics today and jump straight into the microscopic, invisible dance of electrons that literally powers our entire modern world. Let's get right into it.
Have you ever looked at, say, a massive battery pack inside an electric vehicle and wondered, how exactly do we coax that much raw, intense power out of a bunch of static chemicals? It's not magic, right? It's this incredibly elegant, highly structured chemical engine. And to really understand it, we need to zoom way in and look at what's happening right at the atomic level.
So here is our roadmap for today. We'll start with a quick welcome to electrochemistry. Then we'll unpack the redox reaction engine, move right along to understanding electropotential, dive into electromotive force, or EMF, and finally wrap up with the variables controlling cell EMF.
All right, part one. Welcome to electrochemistry. Let's lay the groundwork.
At its core, electrochemistry is really the science of transformation. We're talking about converting chemical energy into electrical energy, and of course, back again. But here is the fascinating part. This transformation happens at a very distinct border. It's the exact interface where an electron conductor, think of a piece of metal, physically meets an ionic conductor, which is your electrolyte. That specific boundary line, that is where all the action happens. It's where the species in the solution engage in this absolutely vital transfer of electrons.
Moving right into part two, the redox reaction engine.
At the heart of literally every single battery out there is what we call a redox reaction. You can kind of picture it as an invisible dance, where electrons are actively transferred between different substances. This interconversion of energies through redox reactions is the absolute fundamental basis of all electrochemical cells. When these electrons basically pack their bags and move from one substance over to another, it actually changes their oxidation states. Now, just as a quick refresher on this dual engine process, because it can be a bit tricky, a redox reaction is essentially two simultaneous half reactions happening at once. First, we have oxidation, which is actually the loss of electrons. That loss drives up the oxidation number. Then, on the flip side, we have reduction, which is the gain of electrons, bringing the oxidation number down. I know, it sounds totally backward, right? But just remember, loss is oxidation, gain is reduction. It is a fundamental, constant give and take. We can see this exact give and take perfectly illustrated when we look at zinc and copper. The zinc loses its electrons, that's our oxidation, and becomes zinc ions. Meanwhile, the copper ions snap up those free electrons, that's our reduction, and transform into solid copper. It's like a perfectly balanced microscopic ledger of give and take.
Which brings us nicely to part three, understanding electrode potential.
Okay, so we know electrons are moving, but what's their motivation? That is where electrode potential comes in. It's basically the natural push or pull a metal has when it comes to its electrons. If you drop a metallic electrode into its own salt solution, it inherently wants to do one of two things. It either wants to shed its electrons right into the liquid, or it wants to aggressively pull them out. Because of this ongoing chemical tug-of-war at the surface, the electrode actually gains a measurable electrical potential all on its own. We call this single electrode potential. It's kind of like a baseline measurement telling us just how aggressively that specific metal wants to participate in the electron exchange. But here's the catch. To compare these different metals fairly, scientists had to create a standardized test, which they call the standard electrode potential. To get this, you absolutely need a pure metal electrode sitting in a unit concentration electrolyte at precisely 298 Kelvin. Locking in that exact temperature and concentration gives us a universal benchmark, meaning we can finally evaluate all these different metals against one another on a completely level playing field.
Moving right along, let's hit part four, electromotive force, or EMF, explained.
So, what actually happens when you connect two of these different half cells together? Well, you're pitting two different natural tendencies against each other. Electromotive force, or EMF, is that final crucial difference in the tug-of-war. It is the literal force that physically pushes the electrical current right through the circuit. Think about it. If there's no difference in potential between the two sides, there's absolutely no flow of current. It's that difference that creates the power.
And honestly, calculating this exact force is wonderfully straightforward. The E cell simply equals the reduction potential of the cathode minus the reduction potential of the anode. Now, because of how standard cell diagrams are traditionally drawn out on paper, you're going to frequently see this written as just the right-hand side minus the left-hand side. Whichever way you write it, both methods get you right to the exact same vital metric.
Finally, we arrive at Part 5, variables controlling cell EMF.
The strict laws of electrochemistry dictate that your battery's raw power output really relies on just 3 distinct variables. First, the actual physical nature of the electrodes you're using. Second, the ionic concentration of the chemical soup inside your half cells. And third, the ambient temperature. That's the whole shebang. If you alter even one of these variables, you fundamentally change the entire capability of the cell.
Which leaves us with, honestly, a trillion-dollar question. If we want to build the super batteries of tomorrow, we're talking about massive grid-scale storage or powering commercial electric planes, how exactly will engineers creatively manipulate these 3 specific variables? How do we push the boundaries of electrode nature, chemical concentration, and temperature thresholds? Because I can tell you for sure, whoever manages to solve that puzzle, they literally control the entire future of energy. Thanks so much for joining me on this explainer. I hope you found it as fascinating as I did. See you next time.